Hello everyone, once again this is PI with Mike, and in this series this is where things actually gets interesting, where we start laying the foundation of getting our model to production. So in this video we are going to start building or I would say writing the building blocks of our API, and we'll be starting that by having our model loading scripts for our API to use. We'll be defining our entities and our interfaces, right? Because one of the importance of we having like a domain layer that we'll eventually see now, which will contain our entities and interfaces, is that it makes our code more maintainable or easily maintainable over time. It makes our implementation align. For example, if we have we use YOLO now, let's say eventually we move to SSD, we won't have to change a lot of things in our code base. Why? Our code follow the clean architecture pattern, it follows the solid implementation pattern, and so on and so forth. So let's go to our code base. So before I proceed, right, I have defined a settings file for our API that will be using throughout the entire program. So entire series, the remaining part of our series, right? We have our settings class where we have our application name that we'll use in our API. We have our version, we have our API version string. We based on when we train, right? If we remember, we saved both ONNX and PT. However, we'll be focusing on PT, which is a direct PyTorch model weight for now, right? Eventually would see how walk through the implementation of using ONNX. So we also have our model version. We also have our confidence threshold. We also have our image size for inference. We also have our class names. We also have our SQLite or SQL Alchemy database, which we are using SQLite for now. Eventually, in subsequent videos, we might consider also using a Postgres database and having the functionality of switching between them. And for our storage for images, right, that we carry out inference on, we would use Hetzner storage endpoint, the storage bucket, storage KID. We would go through the entire process of setting those up. So for now, let's focus on our domain part, where we are going to be defining our entities and our interfaces. What are our entities? Our entities are structures of data that we want to use inside our code base, and to ensure that the result we are getting from one side of our code base is consistent with the other sides that needs it. So, and when it comes to interfaces, right, we are also going to see how important that is. So let's create our domain layer. This is our domain layer. So inside domain, we are going to have entities and interfaces. So for our entities, we want to define our detection and our prediction. Entities want to define detection. We would all see how this come to play out eventually. Detection and prediction. Prediction.py. So inside detection, let's pick a data class. So what is our detection? Our detection is a single bounding box prediction, which is pure data, no behavior. So let's have our data class. At data class, I have to import data class from data classes. Import data class. So we will decorate our class with their data class. So we should all know what the decorator is by now, but if we do not, I guess I'm going to create a series to actually touch on important Python implementation, Python coding with Python, and so on and so forth. But so that we will need to save time, let's proceed. We have a detection. For each detection, as we see now, we say this entity is for a single bounding box prediction. So in that single bounding box prediction, we would have a class ID. If we remember, during training and during preprocessing, we had several classes. Let's pick it up from here, from our settings, so that we can all connect with it. No, we don't even need to pick it up. Let's go into our YAML in data. Let's check our YAML. I think it's in processed. Is it in processed? No. Is it in where is our YAML file? Or dataset.yaml is on our project root. So you see now we have 6 classes, and if we remember, we said apple is going to be 0 class ID 0, banana class ID 1, grapes class ID 2, and so on and so forth. So let's go back to our domain entity here for detection. Class ID is important. We also have the class name during detection. Even if it provides the class ID, it also has the class name, or we can also infer the class name. We also have the confidence, which is the confidence level of that detection. And we also have the bbox. If we remember that this is going to be a list of floats. In our annotation part, whereby we said for each annotation, we have, like, let's say the class ID, and we have our bounding boxes. In this case now, the bounding boxes will just be something like this: 0.1, 0.13 or something, and 0.2, 0.4. But in this instance now, we are not getting normalized bounding boxes. We are getting actual bounding boxes that are not normalized, which we would eventually see. So we go to our prediction now. So in our prediction, this is a prediction, which is one inference run. And what is an inference run? We can have multiple objects in an inference, or multiple detections in an inference. So one inference run, which is what? The uploaded image, what was detected in it, and once, like, an ML engineer reviews it, we also have the ground truth field. We would have to discuss about this. So let's go back to our whiteboard here. So let's assume that we add an inference run. Let's define an inference run here. Inference run. So let's assume that let's pick one of our images here. Let me just pick this. Oh, I don't need this. Okay, let me pick this. Yeah. I need detection, sorry. Let's pick detection, duplicate. I need it. Come here, come down here. So let's say in an inference run, right, I sent this image to our API to detect something, and it came back with something like this. Let me get a text here. So let's say it came back with, like, let's say a class ID of 0. Okay, which means that the class name for that is what? Let's expand this. The class name for that is Apple. It came up with another class ID, and inside Apple we have our bbox for Apple. Let's go back to our entity here. Class ID, class name. Let's say it says this Apple. I have a confidence of what? 0.75 or what? 75%. And it says the bbox of this Apple in this instance not normalized. Let's say the B box is 213 123. Again, just the initial behind it, 109165. And let's copy this to replicate for banana detection. Let's say this is 1, this is banana. Let's say this is 0.55. No, this should be higher actually, because the banana seems to be bigger, but that is not a realistic case. Production is different from when you're actually trying things out. Let's say we have a bounding box of, like, let's say 308. This one is like 223. This one is like 209. This one is like, again, this is not actual bounding box coordinates. This is just for us to get the intuition behind it. So let's say we have this. During this inference run, we have the detection. We showed whoever needs it, either the user to say, okay, yes, there's surely an apple and a banana in this image. They use it to do whatever they want to do, or the end user uses it to do whatever they want to do, right? There is what we call end-to-end ML pipeline. We are going to eventually touch on it, but not in this series, right? So a part whereby as you are carrying out detections, carrying out inferences over time, you still want a system whereby you can easily retrain your model. So what does that mean? Instead of just having an inference pipeline, in this code base, we are going to just build the starting, how would I call it? The building blocks of the review pipeline. What is the review pipeline? While the user is using this to do whatever they want to do, even though they don't have to worry about this, because let's say you send this to the UI now, what the UI will just do, which we are going to eventually see, is that it will just draw a box around this apple, around the banana. What you are using to draw the box on the user interface is these things that you have, and also using the class name to label it. The user is going to do whatever they want to do, but you need to do something. You need to have a different pipeline, a different UI somewhere to say, give me the list of the predictions that has happened so far. So as it gave you and it plotted it, you can then now click on a button that's okay, this annotation is correct. Let's say we have this. Let's say for your UI, duplicate this for me. Yes, let's say this is for the user. Inference one, user. What you are now doing as an ML engineer or an AI engineer is you are fetching what has already been predicted, what the user has used. So you fetch the same thing. Instead of having to say you are drawing the bounding box, you are picking the data manually and drawing the bounding box yourself. The moment you see this kind of thing and you say, oh, this annotation is correct, you just have to click a button that sends a message to your API that mark this annotation as this image annotation as ready to train. So what does that mean? You can have a pipeline job that runs like every 7 days or every 9 days or every few months to say, for the images and annotations that you have reviewed, proceed to training, or automated scripts. So that is one of the important things when it comes to the end-to-end ML pipeline, where you need to set up auto or supervised retraining of your model and deployment. We are going to, I guess I'm going to extend this series eventually, or just create a new series to address moving this to end. But let's proceed. So in our prediction, right, we are going to have our ID, the ID created at, which we are going to see. You don't have to worry about that for now, which are going to be null. These are going to be null until our repository that connects to database, which we are going to see, persists the record, which we are going to see, to a database record and reloads it, passes the record to a database and reloads it, which we are going to see. You don't have to worry too much about it. So now we then have to import from data classes once again. Import data class. We also import datetime for our created at and updated at. Datetime, import datetime. We then have to import our detection from detection. What do we call it? Detection, yeah. From src, which is our src here, dot, which is our domain. Let's close config, close call for dot domain dot what dot entities import what dot detection, yeah, detection, import what, import our detection. So we then also decorate this with data class. Then we say class prediction. Since we said this is like an inference one and we can have multiple detections, we say this is going to be a list. Let's import typing. From typing import list. So this is going to be like a list. Our prediction, we have detections, which is going to be like a list of what? Prediction. So what does detection, sorry, what does that mean? We can have a list of Apple. Let's say we have one with the class ID of 0 Apple confidence blah blah blah, just like we see here. So that's if in this instance now we are going to have 2 detections here. So we then say our model version, which is string. We then say our image URL, which is also going to be a string, and it is allowable to be null, and let's say default to none too. To make this easier, let's just copy this for other places. So we then say ID. Again, this would only be available after we've persisted to our database. ID default to none. We also need actual label, which you might eventually discard, but let's proceed with the flow for now. It should actually be actual labels, but let's proceed for now. Is correct. So this is for our review pipeline to say, oh, for this image, all the detections there is correct, so that when we toggle that it is correct, right, our auto pipeline can pick these images and proceed to training. So none, we don't want to default to false. None is equal to none. Again, it's a boolean, which means it is either true. It is either no. It is either true or false, and we don't want it to be false by default. That is wrong annotation. So created at, which is going to be date time, but can be none, and default it to none. We also need to have reviewed at for when we reviewed it to say, oh, this prediction is false or true. So reviewed at date time default to none is equal to none. So we have our entities now. So we have to move to interfaces now. So in interfaces, we want to define a model runner to run our model to get predictions. Model runner. So again, our interfaces is what our code would actually implement, right? So I would see that very soon. We have a prediction store. So let's go to our model runner. What's our model runner? We are going to have anywhere you see I before. This is going to be our IModelRunner. And what does that tell you? The I there tells you that this is an interface for our actual model runner. So, which means it is the contracts for anything that can run raw inference on an image and return predictions, detections. So our SRC core depends on this. So let's import from ABC, import ABC. Now ABC, as we should all know, is what we call our abstract class. It is what another class inherits, and it needs to implement the methods that are there. We are going to see it. Abstract method. Yes. Then we define our IModelRunner. Which is going to be ABC. We then say we then now say our model runner must have a run inference at abstract method, and our model runner. This abstract method means any class that inherits this IModelRunner interface, they must all have a run inference method, even though they have many others. Run inference. Then we have ourself. We have our image part. It needs to take in the image part, which is a string, and it needs to return. So we need to return a list of detection results. And I guess we have to import our detection from. Let's just copy this from entity, so we don't have to untype it. So let's use from typing import lists. Yes. So we then say this is to ensure this is to run the model on the image and return raw unfiltered detection. The role of this method is to do this. We also need to know something, that confidence thresholding, which we'd eventually see, is a business rule. And should only be in core. Okay, so now we need to have our interface for prediction store. So our prediction store now. Our prediction store is the contract for persisting and retrieving predictions. It is implemented by our prediction repository, which we'd eventually see, which uses SQL Alchemy. All methods are async. Important. Async. And the each repository method opens up an async session. Open an async session per call and drops it immediately, so it never holds it. Let's make this multi-line. Okay, so we also import our ABC. Let's also import this. Do we need the list? I'm not sure, but let's import it. So we also have to import prediction also. So from src domain entities prediction import our prediction. So we then have to implement our prediction store class prediction store. Then we also have it as our abstract class, and we have 3 abstract methods. Abstract method async def save, Yes, we have the self, we have the prediction, which is what? Our prediction. And it also returns back the prediction that it saved. Return the prediction that you saved. What does this do? It persists a new prediction and returns it with the new ID created at that has been populated. So let's just copy this to make others easier. So we then need to have get unrevealed, which we are not completing. So this would have a limit and an offset. Limits should be which. Now the reason why we need to have limits is that, for example, let's say we already have 1,000 predictions that are unrevealed in our database. We don't want to fetch all of them at once, which is why you see when you're loading a page, you see several pages. So we are going to we may eventually see how we convert our limit and offsets to pages. But take it for now that let's say you want to get at most 50 unrevealed detections or 50 unrevealed predictions, and you want to instead of getting the top 50, you want to get the next 50. So which is why we have offsets. So our limit is what? Integer, which is what? 50. Then offsets is also an integer, which should be default to 0. So what does this mean? Let's even look into it. So for example, if I say every page should be 50, so that means the first page should be what? It should not offset anything. So offset will be, let's say page 1. Page 1 will be limit should be 50, and offset should be 0. Offset should be 0. But for page 2 now, page 2 would be limit is also 50 because we want 50 per page, but offset will now be 50. Offset will be 50. Let's go forward. Page 3 would still be limit is equal to 50 because we want 50 per page. Limit is equal to 50, but now our offset would now be 100 because what is our page 3? 100 rather. So this is why we have limits and offsets, and this will be returning not a prediction, it will be returning a list of prediction. A list of prediction. So we then for now let's ignore our update prediction, or let's just add it actually. Update review rather. Update review. So it takes in the prediction ID, which is our ID from here. Prediction ID. Our prediction ID is actually UUID. So that would be a UUID, and we'll take in. We'll see why our prediction ID is UUID now. And let's go back to our prediction here. It's a UUID. So let's import from UUID, import UUID. So we are changing this to UUID. Okay. So let's come back to our prediction store here and say let's import UUID. Okay, so we take in our prediction ID, we take in our is correct, if it's actually correct, to be bool. So it tells us that, oh, is this prediction for this image correct or not? This returns none. This does not persist actually. This gets or fetches fetches predictions from database with unreviewed. Is it unreviewed? Let's check our entity now. Is correct. No, not is correct. Where our reviewed at is none. Thank you. With reviewed at none, meaning it has not been reviewed. None. Okay. So what does this do? It records an ML engineer or reviewer's review to say, oh, is this prediction correct or is it incorrect? So we have our model runner, we have closed out our domain layer now. Before we end this video, let's proceed to actually implement our model loader. So let's get and before I start this video, right, I have created a logger class, right, for us to call anywhere. Instead of having to import logger everywhere, we have this set up in a way that we can just call our get logger. We use it in the entire implementation and in our entire API, and instead of having to print in several places. So we can also set levels. So let's have our model loader. So what is our model loader doing? It loads our model during startup. Loads our model during startup. And we then use the loaded model to make predictions. Okay, so let's now import our data class from data classes. Import data class from pathlib. Import paths from typing. Import what? Any lists, dates, literal, optional. Then we import our logger now from utils.logger. Import get logger. Then we say our logger for this file is get logger. We then say our different type of model format should be what? .pt, literal of .pt of ONNX or pt. Okay, so we then have to define our model bundle, data class model bundle. Our format is equal to what? Model format, and our model should be any data type, which is going to be our model. Okay, so we then have to define our load model. Def load model should take in the settings of the API, which we'll eventually see, and return what? Return a model bundle. So we then do requested which is model format is equal to settings dot model format dot lower. Let's confirm our settings file again, which is what? Model format. So we are right on track. The lower Then we then do if requested is equals ONNX. Bundle should be okay. Now try load ONNX, which we are going to define, and should take in the settings. So let's proceed to defining our loading of ONNX and loading PT. So we then have to define try load ONNX, then take in the settings. Settings should return a model bundle or none when not available. Okay, so we then do ONNX path is equal to what? Path settings dot ONNX path weights, ONNX weight path, sorry. Then we now say if not ONNX path dot exists, then let's just tell the user that logger.warning warn the user or warn you that ONNX weights are unavailable. Weight not found at our ONNX paths. So it returns none. But if it exists, it will try to import our ONNX runtime, which I don't think we have yet. Import ONNX runtime as ORT. If it does not exist, except import error as, or let's just not use E since we already know the error. Another logger.warning. Let's copy this so we don't so ONNX runtime is not installed. But if it can pass this level, what does that mean? But return none. If it can, it's effectively load ONNX, so we can just try providers is equal to, we need to have different providers for when we have cuda. So cuda execution provider and also CPU execution provider for when we do not have GPU provider. Then if cuda execution provider, let's just copy this so we don't have to untype that. If cuda execution provider in ORT.get available providers. Again, you won't know this until you go through the documentation. Then else CPU execution provider. Let's copy this. So what does that mean? It means that we are checking, do we have cuda in our hardware where we are trying to run the model. If we do, it means we have these two providers available for us to use, for our model to use. And if it does not, we only have our CPU execution provider. Based on that, we then create our session. Is auth.inference session. Then our string of what? ONNX path. We are converting it to string, not path anymore. Then providers is equal to what? Our providers. So we then do our logger.info. Now we've effectively loaded our model. Loaded our ONNX from our ONNX paths using our providers. Our providers are 0, our GPU or our CPU execution provider. We then do what? We return our model bundle with format is equals to what? ONNX, and what? Model is equal to session. Okay, so or if there is an other exception that we did not account for, except exception as E, we then log another warning, logger.warning, or let's even use logger.error. Yeah, this is an error. Logger.error, failed to load model or ONNX model. Then let's see our error in the terminal. We return none. So let's use this pass to also account for our PT model. Def load PT. Load PT, it also takes the settings and also returns a model bundle. So we then say PT paths. Let's just fetch this so we don't have to untype all those since we have it. So this is going to be our PT paths. So our PT path, this is what? Our PT weight paths. PT weight paths. If not PT weight, PT path.exist. Yes. Then we say, I don't think we want to log this. Let's just raise, since this is an important part, because even if we select ONNX and it does not exist, it returns none. We want to always try to ensure we load our PT. So we are instead going to raise a file not found error. Then say CO weights not found at the PT paths. Ensure you have your PT model. So if the model exists, we then do import torch. We then do from Ultralytics, import YOLO. Then what else? We then do device. Let's move this one more line. Device is equal to cuda if torch dot cuda dot is available, like we did, else just default to using CPU. Don't worry about GPU. Then we then do model is equal to YOLO and string of our parts, PT parts. Then we then do our model dot to our device. Then we then do logger dot info. We've loaded our PT model. Model loaded our PT on device from our PT parts. Okay, we then return our model bundle. Model bundle format is equal to pt, then what? Our model is equal to model. So let's conclude on our load model implementation. So we said this should try to load ONNX. So if bundle is none, yes, or if bundle is not none, rather, if it's not none, just return our bundle. Then we then have to do our logger dot warning since the bundle is none, unable to load requested ONNX formats, defaulting to pt. So we then return our load pt with settings. So we now have our model loader. Let's try something. Python. Instead of running, let's close this. I can try to run this Python file. Where do we have it? Let's say Python what? Our src. Then our infrastructure. Infrastructure. Our ml. Then model loader.py. It will not run. Why? We are already building it as a package. Oh, let's see. Where is our... Oh, we have a bug in there. Line what? Line 71. Oh, this is if. In fact, even if it runs, it cannot find a module. So we have to run this as a module if we want to run it. Even though it will still not run now since we are not calling it. src, this is what we're going to use to run any separate files we want to run eventually. But for now, let's leave it. So we have our src.infrastructure.ml, model loader. The .py should not be there. So it says it can't open file. Model loader. Okay. Oh, the necessary init files are not there, but let's ignore those for now, and let's proceed. So normally we are supposed to have our ONNX and TorchRunner, but let's just build our TorchRunner for now. Let's say our TorchRunner .py. Oh, we already have it. Oh yeah. So let's now do this. We've imported YOLO, we've imported Torch. Let's import our entities from src.domain.entities.detection. Let's import our detection. Oh, I didn't type imports. Import detection. Let's also import our IModelRunner from src.infrastructure.interfaces or interfaces. Is it interfaces? Let's confirm. Oh, interfaces.modelRunner. So that our TorchRunner aligns with our interface. Import IModelRunner. So we then do class TorchRunner. Again, we should have this inherit our IModelRunner so that we will be sure that everything our interface needs, our actual implementation has it. So we then do our dev init, our class constructor, we have our self, and we have our model, which can be any, but okay, it cannot be any. Our torch now is going to be YOLO. Sorry, YOLO. This is not our ONNX model runner. So it will be YOLO. This is going to return none because our class constructor and we don't need to return anything. None. So we then say our self.model is equal to our model. Okay. So we then do our def, run inference, the method that our IModelRunner wants us to implement. So run inference, we take in the self and we take in our image parts. So which is a string or a byte or whatever, but we eventually update that as needed. Let me import lists from typing import lists date any optional, since we may need all those. So this is going to be our detection. Then we then do detection, or let's say our result is equal to our self. Let's make this model local to this our TorchRunner. Self.model dot predict according to YOLO library image parts, then conf. Do you need to pass conf? Let's leave conf since we don't need it here. Verbose is equal to false. We'll see why that is needed eventually. We can do our logger. Let's import logger here. From utils.logger import get logger. So our logger is equal to get logger. Then we come here and say logger.info. Logger results for us. Torch model inference results is what? Our results is actually result. Let's make it results. So let's have our format string here, and let's initialize our detections is list, like we said, list of what? Our detection default to empty list. So for R in results, because I know the documentation which we are going to see, we then say for box in R.boxes, our B boxes, we then say detections dot append detection. We then have this as class ID is equal to our int of what? Box.cls according to the documentation. We then have our what? Class name is what? Our r.names. We have to get this is used to being a dictionary, right? So we have to get the class name for this class ID. So we then have our confidence is equal to float of what? Our box.conf according to the documentation. We then have our bbox as what? According to documentation, that is our box dot xyxyn, yes, 0 dot to lists, which we are going to see. Yes, we then do what? After the loop is on executing, we then return our detections. So in our next video, we are going to see how this starts coming together, and we are going to run our model inference. See you in the next video. Don't forget to like, share, and subscribe.